Once you've fitted your regression model, of course you can measure R-square and then say you're ready, so you know whether R-square is good or bad. But to have much more confidence about what your model actually tells, and even more if specifically if you're using the model for measuring the strength of relationship, you do need to know more about the regression parameters. So from those you can actually read how important your variables are or which ones can be dropped out and so on. So the residual of a fit is a difference between the data and the model values that we already discussed. And so, of course, that's given like this. So it's our vector of observations minus our data matrix multiplied with the parameter estimates. So these values should be compared to the size of experimental error or the noise in the measurements. So in the simple and most typical case, we may suppose that the noise level is the same in all experiments. So the noise should be estimated by replicated measurements. So the measurements which are repeated several times in the same experimental condition. And the size of noise is expressed as the standard deviation, sigma, of the repeated measurement values. So the basic statistical requirement is that a model should fit the data with the same accuracy as the measurements are obtained. So the residual of the fit should roughly equal the estimated size of measurement noise. So here is the relationship. And in graphical way, this is what we mean. So if now we have our measurement data and we have the residuals in here, so the way they vary away from our regression line should be at the same level as if we replicate our experiment for a single setting of whatever phenomena we are measuring. So that variation in here for the same situation should be corresponding, should be same order as the variation of the whole fit. So now if you recall the least square estimator for the coefficient, so it was represented by this equation. So since the data y contains noise, then of course the values of b, so the estimates, are noisy as well. And the standard deviation of the coefficients may be calculated by the so-called covariance matrix. So if we calculate covariance of our parameter estimates, which could be done using this formula, so then the diagonal of the covariance gives the variances of b parameters. So of course, standard deviation for each coefficient is obtained as the square root of the diagonal values of our covariance matrix. And the signal to noise ratio, so the calculated value of coefficients divided by the standard deviation of it, is called t-value. So in here, if we take every parameter estimate and we divide it by its own standard deviation, then we are obtaining t-value for that particular parameter. And the t-values may be used to select the terms of a model. The idea is that if a term is not known reliably enough, it should be dropped out from the model. And this is the situation if the uncertainty, so the standard deviation of the parameter estimates, is large when compared to the calculated value of the parameter estimate itself. Now, if you are not a math person, you just go by the rule of thumb. So quite often people in chemistry or other related disciplines, they would use a rule of thumb that t-values smaller than 3 indicate non-significance of a given variable. So that means that any explanatory variables whose t-values are within plus minus 3 should be abandoned from the model. But of course, if you're a perfectionist, if you're a mathematician, then the rule of thumb will not be enough for you. So in that case, we need to convert each of the t-values or t-statistics into the respective p-value and use them to decide on significance of each. So then the null hypothesis in our test means that the particular bi estimate is not significantly different from 0, and we are looking for evidence to reject this. So that means that small p-value, so for instance, p-value less than 0.01 would indicate that we have very strong evidence to reject this null. So consequently, small t-values would mean high p-values, and the other way, high p-values would mean small p-values. So high t statistic and its low p-value means that we may consider that particular variable as significant for the model. Now I used here the example of 0.01. Most commonly 0.05 is actually the one chosen. So we would remove from the model any variable for which the p-value is above the desired significance level. And what is important in here is that sometimes including a very irrelevant variable may distort the estimates for the other variables. So that's why a good way is to do stepwise correction of the model. So if you have many variables, then you pick the one which is least appropriate or which has the highest p-value, you remove only that one and you fit your model again. Because then the estimates, the t-statistics and the p-values and the estimate values will change for all the other variables. And it may mean that something that has not been significant before will now become significant once we have removed the very irrelevant variables.